Okay, welcome back from the break, everyone. Everyone excited to get back to biostatistics? All right. Yeah. Yeah, it's best to keep the momentum up and go straight through to the end. I think that the rest of the course is going to be kind of fun. Everything we're doing now is stuff that you can directly apply to your project, which I just posted this afternoon, which is going to be lots of fun. It's real data. I got the data from the New York City Community Health Survey, the most recent one, which was in 2013, posted the real data for you and put an example question up for you, also an Ebola data set that I found, and I'm leaving the floor open to you as well to pick other topics if you would rather. So take a look, we'll talk about it lots, I'm sure. The important thing to remember about it, it's not like an assignment or an exam where I'm expecting right or wrong answers. What I'm really going to be grading you on is the quality of your presentation and to see that you've done a thoughtful job. That's all that matters. So there are different ways to do some of these projects. There are different projects you can do. But if you put together a good presentation and I can see that you're aware of the statistical issues and make a good presentation of your descriptive statistics and such, you will do well on the project. So we're going to continue. Yes, question. Question is, how many assignments are you going to have? It's in the syllabus. I think you only have one more assignment left. And that's just because there is a fair bit of material after the after the break and after the last exam that I still want to make sure that you know and you won't necessarily use on the grade, but the pace of assignments is slowing down because you'll have plenty of stuff to do for your project. Yes, another question. If we're working on something at our job, we're recollecting data for a study, are we able to review that information with you to see how it can become, or if it's possible for it to be part of the final project? Yes, so question is, if you are, if you have data through your job, can you use that for the project? And the answer is unequivocally yes. I think that's great. If you're not sure what to bite off for the project or whether it's appropriate, let me know and we can talk about it. But yes, I really welcome people bringing in their own data to this. It makes it interesting. It makes it valuable for you. You'll have a chance to work on it as part of class and to get feedback on it from your professors in the course. Another question.
I know that you've given us before exams, you gave us like practice tests too. Now with this case, this is a project. You did give us like a mock type of project, like like a dummy type of project, just to see so we know how to do it. Because there's no one particular way, but sometimes people are always visual to see. You know what I mean?
Yeah. So, question: could I pose like an example project? And yeah, I think I could do that. I'll find one from a previous semester and anonymize it and show it to you.
It's a clearer map, basically.
Yeah, I'd be happy to do that. Any other questions about the project, about the exam or makeup exam before we get started? It was a tougher exam. Don't feel bad. Everyone had a bit of a tougher time on this one, and I scaled it up. There may be a scale at the end of the semester as well, but most of you made it through reasonably well. The average was over 80 anyways. On this makeup exam, if you do it, it'll be like the other one. It's like an assignment. I'll take the average of your final grade on the assignment and the exam, and except this time it's a little bit of a shorter assignment. I gave you 90 minutes and 4 attempts, so you can really get it down if you were doing that. All right. So, hypothesis testing 2. But before that, there's an event at the school here this week that you should know about. It's on Friday, 4:30 to 9:30. I'm not sure I can make it this Friday. I'll try to make it at least to the beginning of it, but I want you to know about it. So today, we're going to review a little bit the type 1 and type 2 error, and then I'm going to introduce the concept of power to you. And that's something that I had intended to cover last class. We didn't quite get to, but it fits in just as well with this class. And then finally, I'm going to introduce the t-distribution to you, which we've been alluding to on and off, and we're finally going to delve into it and show when to use it and how to use it, both for confidence intervals and hypothesis tests. There is a new concept called degrees of freedom that you're going to have to be able to calculate for t, and other than that difference, the calculations are going to be pretty similar to what you're used to. Just to review, the steps of hypothesis testing, they're the same for all the hypothesis tests that you do. You start by stating your hypothesis and setting a significance level. You take your sample of size n, compute a test statistic. Before it was z, now it's going to be t, and you're going to choose an appropriate distribution, either the normal distribution like we were doing before, or the t-distribution like we're going to do today, and then determine a p-value and make your conclusions and decide whether to accept or reject the null hypothesis. You'll remember that for two-sided tests, not for one-sided tests, there was an equivalence between confidence intervals and hypothesis tests. That is, if your confidence interval includes the value of your null hypothesis, then you don't reject the null hypothesis. And that's going to hold also for the t-distribution. And you'll recall that with when we were the hypothesis tests and the confidence intervals that we were building before relied on the central limit theorem. And you remember that the central limit theorem related the population distribution to a sampling distribution. It said that if you know a couple of things about the population, that is its mean and its standard deviation, then for large enough samples, you know what the distribution of means of samples of that size are going to be. The mean of those samples, so the mean of the means of the samples, I should say, is identical to the mean of the population, and the standard error of the means of those samples was related to the standard deviation in the population by this factor of square root of n. And the key thing there was that for a large enough n, that distribution of the sampling means is normal, regardless of what the population distribution is. So we're gonna relax that assumption in a couple of ways. We're gonna go towards small samples today, and we're gonna require that population distribution is normal. So it is a practical, real life application where we don't necessarily have large samples and we don't know everything about the population. Here were the formulas that you used just as a review for constructing the confidence intervals and for performing the hypothesis tests. And I'm just putting these up here so you'll have them handy for review, and you'll see how similar they are when we start using the t-distribution. So you all remember this, the relation, the type 1, type 2 error. Type 1 error is the one that we control with alpha. That's when the null hypothesis is true, but we reject it anyways. So if alpha is set to 0.05, there's less than a 5% probability of that happening. So if the null hypothesis is true, then only 5% of the time are you going to find a test statistic that would lead you to reject the null hypothesis. Then there is the type 2 error, which is where actually the null hypothesis is false. Our alternative hypothesis is true, but we fail to reject it. So you remember that in general, we don't reject the null hypothesis unless we have abundant evidence to reject it. So if we don't have enough evidence to reject it, even when we should have, that's a type 2 error. Type 2 error can happen because we either because we got lucky or we got unlucky, or we didn't have enough data to be able to have enough evidence to reject that null hypothesis. So in that analogy of the courtroom trial, if the defendant is guilty but you fail to convict, that could be because you just didn't have enough evidence. So it doesn't necessarily mean you've proven that the null hypothesis is true. And then it's also possible that you make no error by rejecting or failing to reject the null hypothesis. So you're all comfortable now with hypothesis testing, right? We perform the hypothesis test by assuming that the null hypothesis is true, that H0, and then calculating what's the probability of observing our test statistic or something more extreme, assuming that the null hypothesis is true. When we do a power calculation, we go at it differently. We actually take some alternative hypothesis and assume that that is true. And assuming that is true, we calculate what would be the probability of rejecting the null hypothesis. So we go about, if we say, okay, what if there is a difference? Now, what's the probability of us correctly rejecting that null hypothesis? And I'll show you what I mean. And I'm going to try drawing it out here first, just to take my time with it before you'll see on the notes it's actually drawn on there. But I wanted to try drawing it here. So here's H0. This is, let's say cholesterol. Oh, shoot. Oh man, I lost it. Okay, let's try that again. So under the null hypothesis, we have a normal distribution . H0 mu equals, I don't know, what's our null cholesterol level? 200, let's say. Now you'll recall that then when we go to do a hypothesis test, we'll take a sample, we'll calculate its mean, and then find out if that mean lies within the rejection regions of this null sampling distribution. So it's going to be in these tails. Let's say z equals minus 1.96 and z equals 1.96. Ah, okay, I give up. That doesn't work. I'm just going to show it to you. So blood pressure instead of cholesterol. Under the null hypothesis is that the mean blood pressure is 130 and a standard error of 2.5 for the given. So it's a standard error of the sampling distribution. So we've got these two rejection regions out here and here. Now, when we do the power calculation, we're going to say something else. We're going to suppose that in fact the true mean of the target population is 132. So it's 2 millimeters of mercury different than under the null distribution. So if that's the case, if it's 2 millimeters, or if it's 2 millimeters different, so the mean is 132, then 95% of the time, whoops. So we're going to start with this assumption that the null hypothesis is true. And remember that we're going to reject it if we get a mean that is outside these two critical regions, the minus 1.96 and 1.96. And now under the assumption of this alternative hypothesis, we can calculate the probability of getting a value in one of those two regions. Okay, so we're assuming that the alternative hypothesis of the mean of our target population, the mean blood pressure, is 132. And then we're calculating the probability of correctly rejecting the null when we're doing a hypothesis test. So this overlap that you see here is the lines are drawn according to the null hypothesis at, say, z-scores of minus 1.96 and 1.96 under the H0 distribution, but then the power is calculated using this alternative distribution. So what's going to happen if we move this alternative distribution further to the right? What's going to happen to this area? See if I can at least draw a little bit here. So let's say it's so what's going to happen to that probability of correctly rejecting the null hypothesis if that's the correct distribution? It's going to go up, right? Yeah, it's going to look like it's going to be more like 50%. So this would be a power of about 50%. Still not a very good power. It means that if this is your null or your alternative hypothesis, you only have a 50% chance of correctly rejecting the null hypothesis. Yes.
So just a quick question to clarify, is the null hypothesis average equals 130 or the average equals 132?
130.
Okay.
Yeah, this
So
is the null.
alternative is that the average doesn't equal 130, or the alternative is the average equals 132?
So under your hypothesis test, the alternative is just that the mean is not 130.
Right.
Right. So this it's probably actually better not to call this HA, because this is not a part of your hypothesis test. This is like your alternate reality.
Okay.
This is what you're going to hypothesize that the true distribution of your target population is based on a previous pilot experiment, or based just on some kind of assumption.
So, where would you have gotten the 130 to begin with? Like that number based on the pilot study?
No, the 130 would be based on, like, you know, your previous large study or the population as a whole. That's, you know,
so this would be for more of a specific group.
this one on the right, this would be for some specific group.
Okay.
So the H0 would be like, this is the population as a whole. The H, you know, this would be like, we have smokers, we have people with 3 or more dogs in their households. You know, we are gonna do some kind of study to see if they're different than the null population.
So don't call it HA.
Right. Yeah, let's just call it your alternative reality for now. Yes.
So is it right to say, can we think about it that the more different that alternative reality is from the null hypothesis, the more likely you are to reject it?
That's right. That's right. So the more different it is, the more likely you are to reject the null hypothesis. Also, the more narrow this distribution is, the more likely you are. So let's suppose actually, that's not a good place to do it. I'm going to clear this now. Now let's suppose okay, there's one alternate reality. Here's our power. It's getting pretty big now, right? Now we have a power of something like 90%, because it's more different from the null hypothesis. And here's another one with the same mean, but a narrower distribution. How could that happen? How could you get this instead of this? Yeah.
Increasing the sample size.
Increasing the sample size, absolutely. That's the most likely way you would do that. So we've increased the sample size, so we've decreased the standard error in our hypothetical reality here, in our experiment that we haven't done yet. That's the key thing about this. This is when we're doing power calculation. This is a study or an experiment that we haven't done yet. So that's why it's a hypothetical alternate reality. So what happens to the power here with this smaller standard error compared to the larger standard error? Anyone? Oh, it increases. Thank you, Emily. Yeah, the power here now is looking like it's close to 100%. If this is true, there's almost no chance that you're going to get a mean of your sample that is not within the critical rejection region. So you've got a power of almost 100%. Any questions about this? You'll get to practice this some more in lab, but the important thing is that I want you to understand what a power calculation is, because power calculations are important. You'll hear about them if you're ever involved in planning a study. People will talk about what's your power, you know, is your sample size big enough to detect this difference? And this is the concept of where it comes from. There are power calculations for different kinds of tests. It's not always as easy to visualize as this, although it pretty much is. These are the sampling distributions, and it's a comparison of overlap between your null hypothesis, your sampling distribution under the null hypothesis, and the probability of getting a sample that lies in the rejection region, given some kind of argument about your target population. So, any questions? Yeah.
Before you make the statement, the more different it is, the more narrow distribution is, the more likely you are to recheck it. Saying the difference between null and the alternative.
Yeah, or the difference between the null and the target population. The bigger the difference between the mean of your null hypothesis and the mean in your target population, the greater your power would be. Or the smaller the standard error in your sampling distribution, due probably to larger sample size, or to a less variable population. The smaller your standard error, the greater your power. So power is just 1 minus the type 2 error, because remember, type 2 error is, okay, if your alternative hypothesis is true, you fail to reject it, that's a type 2 error. But if you do reject it, probability is 1 minus that type 2 error, that's your power. So power is 1 minus beta. And that power increases as your alternative mean gets further from mu0. So mu1 here, if that would be, say, the mean of your study population. And the power increases also either as the standard deviation of the observations in the population decreases or sample size increases. Both of those things cause a reduction in the standard error. So those are, yes. Beta is the type 2 error rate. So beta is the probability of accepting H0 when the alternative hypothesis is true. So these are the really important things to know about power. I think more important even than being able to calculate them, because there are tools to help you calculate them, but there aren't tools to help you understand what it means. So the type 1 error rate stays fixed regardless of the alternative mean or the power. The type 1 error rate alpha is something that we just set. And power is something that generally we either calculate the power for a given sample size, or we calculate a sample size needed to give a certain power. Power is, as the name kind of implies, you want more of it. So the more, when you're going to plan a study, you want to plan a study that has as high a power as possible to detect the difference that you're interested in. And typical values are 80% or 90%. not for any particular reason. Sort of like alpha equals 0.05, it's kind of arbitrary, it's just commonly used. A power of 80% or 90% are commonly used as well. So does anyone want to tell me in plain language, suppose we're planning a study to say whether whether smokers have higher blood pressure than non-smokers, and we're planning a study that has 90% power. What does that mean? Yep.
The chance that the blood pressure of the smokers is different from the population
So
blood pressure
you're very close. Remember, there's the hypothetical bit in there. So it is that if there really is a difference in the blood pressure of a certain amount, the chances of us being able to detect it in this study are 90%. If there's no difference, then we don't expect to detect it. So because it's 1 minus the type 2 error rate. So it only applies when there is in fact a true difference. And it's to protect us, it's from not wasting money and time on a study that where even if there is a real difference, we're not going to be able to see it. So you would start out by saying we want to be able to detect a difference of 2 millimeters of mercury. Assuming that there is really a difference of at least 2 millimeters of mercury, if we observe 100 subjects, this is our probability of rejecting H0. If there isn't a difference of that 2 millimeters of mercury, then all bets are off. That's fine. We don't want to reject the null hypothesis then. It's not a type 2 error to accept the null hypothesis if it's true. Oops. All right, one more summary. We've covered these. Actually, I guess one thing that we haven't covered is this increasing alpha. If you this is actually a little bit unclear. Let's call this smaller. Oh, jeez, that's so hard. I meant increasing the significance level, which is actually a smaller alpha, right? So let's call this decreasing type 1 error rate. That's clear. So that means that you have to be more confident in the alternative hypothesis, so a lower probability of type 1 error in order to reject it. So if you're requiring a higher standard of evidence, you're less likely to be able to observe that standard of evidence, all other things being equal. So if instead of alpha equals 0.05, you go down to alpha equals 0.01, does your power go up or down? Thumbs up or down? Yeah, I see one thumb, you're right. Any other thumbs? So we've lowered alpha from 0.05 to 0.01. So if we keep all other things equal, we change alpha from 0.05 to 0.01. When we make alpha 0.01, is the power going to be higher or lower? No. Yeah, power is going to be lower because it's harder to find enough evidence to reject H0 at alpha equals 0.01, right? So you're less likely, even if the alternative is true, you're less likely to reject it because you're requiring more evidence, so your power goes down. It's kind of unintuitive, eh? Let's see. How about, yeah, yes? Uh-huh. Yeah, okay, so what does it mean to lower alpha from 0.05 to 0.01? That means that if the null hypothesis is true, instead of incorrectly rejecting it 5 times out of 100, we'll only incorrectly reject it 1 time out of 100, which means to be that much more confident in rejecting, to have that much less of a chance of incorrectly rejecting, you need more evidence. So, or for the same amount of evidence, you need a more extreme sample. It's going to happen less of you know, there's more chance that you will get a sample that does not lie in the rejection region. So, you know, under looking at this, when you know, if we have an alternative, you know, or our target population has, when we sample it, it has a distribution of mean blood pressures that really is on average different from the null hypothesis. It's still, you're still not going to reject your null hypothesis all of the time, because sometimes you'll get a sample with a lower mean, sometimes you'll get a sample with a higher mean. When you happen to get a sample with, even if these are really different, every now and then you'll get unlucky and find a sample with a small mean that you don't, where you don't reject the null hypothesis. So again, the alpha, the type 1 error rate, that is when the null hypothesis is true, how frequently you reject it. So lowering that alpha means that you incorrectly reject the null less frequently. But the flip side of that is you're widening, you know, you're saying it has to be further from the mean of the null distribution in order to reject it. And the trade-off that you make there is that even if the alternative is true, you're going to fail to reject it more often, because you're creating a bigger area, a bigger range of blood pressures where you don't reject the null. Yes?
So basically, like if the null is 130 and you had you're saying that you think the blood pressure is like, say, 160, your alpha would be really, really small. But if you say, you know, you think the blood pressure is 132, they overlap more, so it's harder to tell.
So first thing, if in your target population the blood pressure is 160, it's your beta that's really small. It's your type 2 error rate that's really small.
Oh, right, because alpha would be really high because you're like, they're definitely different.
Well, alpha is just fixed. Remember, alpha is the type 1 error only happens if actually your target population mean is also 130. So if the true target population is 160, a type 1 error can never happen, because a type 1 error is the probability of rejecting the null when the null is true. If the null is not true, it's impossible to make a type 1 error.
Can you just do a quick review one more time?
Sure, sure. So let's go back to the previous page. When you're hypothesis testing, there's a lot of hypotheticals involved in hypothesis testing. So when we're doing a hypothesis test, the z-test, the t-test, we assume that the null hypothesis is true. So our study population is no different from everybody else, for example, or if we have, a case and control, they're no different from each other. So you assume that there's no difference and calculate the probability of observing something that is as different or more different as what you see. So when you do a hypothesis test, you just draw one distribution, this null distribution. You pick places out on the extremes of that sampling distribution. And then if you get a sample with a mean that's out in those tails on the null distribution, you reject. And that's your hypothesis test. So there's just, in your hypothesis test, there's only one distribution, the null distribution. One sampling distribution, I should say. Now, in a power calculation, we actually are thinking about two distributions. We now are going to assume that there really is a difference, because remember, we assume that the null hypothesis is true when we're doing a hypothesis test, but when we're doing a power calculation, we assume that there is actually a difference in our target population from the null hypothesis. So we assume what that difference is, and that's just an assumption, or it's based on a pilot study or something, but you have to make that assumption on a study that you haven't even done yet. That's kind of the catch of power calculations. You make some assumption that if there is a blood pressure difference of 10 millimeters of mercury from the null hypothesis, then what's the probability of rejecting the null hypothesis? And you can do that by saying what are the rejection regions of the null hypothesis, and then doing a probability calculation under this alternative distribution that we've assumed. So under, remember that type 1 error, which is what we control for with hypothesis testing, can only happen when the null hypothesis is true. Type 2 error, which is the thing that we're controlling with a power calculation, can only happen when the null hypothesis is false. So those are kind of that's the big difference between hypothesis testing and a power calculation. Good. Uh-oh. The screen stopped showing. I hope not. So this was from a while ago, but yes, as alpha goes from 0.05 to 0.01, you decrease your power, because there's a trade-off. You make it less likely to make a type 1 error, but you make it more likely to make a type 2 error. Okay, I'm going to try to see what's wrong with the image here. That's weird because we're looking at it right there. Huh. Yeah, no. Okay, sorry everyone online. I don't know why you've lost your image. Seems to be something wrong with YouTube because we're still broadcasting. You are watching the Google Plus broadcast here, but not the YouTube one. Okay. Let's try it from this one. Okay, that looks good. Oh, and it's back. So okay, I think we're back, everyone online. It's working, okay. It's good to see everyone online is paying attention. Oddly, I'm pretty sure that that was not our fault. That was a minor hiccup in Google there. Okay. Okay, it's time to introduce you to the t-distribution. We've been focusing so far on the normal distribution and large sample sizes because it's a perfectly good model to explain to you hypothesis testing, sampling distributions, power, all of this stuff. And now it's time to start extending that to other types of studies. So in order to use the normal sampling distribution like we've been doing, we have to either have a very large sample size or a normal population where the standard deviation is known. And any time where we have a smaller sample size and we don't in fact know the standard deviation, we estimate it from a sample, we're going to use the t-distribution. And as a historical note of interest, it was someone, William Gossett, who worked for Guinness, who developed the t-test. And it's called the student's t-test because that was a pen name that he used to publish it. He wasn't allowed to publish as an employee of Guinness because it's a corporation, and so he made up a name and published it anyways. And it was important for beer, I imagine, because they would first make small batches to test out some process and want to know. So suppose we measure the alcohol content of these 5 small batches of beer, we want to know if it's changed from the usual that Guinness is supposed to be. So, you know, there's some variability from one batch to the next, but we don't know if it is a cause for concern without repeating it a couple times, measuring the variability, and saying whether it's actually different. And that was the real life application that led to development of the t-test that we now use for everything else you can imagine almost. And by the way, the thing that it came out of was that he noticed that with these small batches, so a small number of observations, the variability was actually greater than you expected from your standard error calculation. So he was rejecting his null hypothesis more frequently than he should have, even given if there was no difference in the brewing process. The way that we go about using the t-distribution, it's very similar. You calculate a t-statistic in exactly the same way as you're accustomed to calculating the z-statistic, and the only difference is this, that you use a standard deviation that you estimate from your sample rather than a known standard deviation from the population. It's very practical because most of the time you don't actually know a true standard deviation, you can only estimate it. And then the standard error, you can calculate in the same way, and you get your t-statistic in just the same way. So this is divided here by a standard error. The only difference is that when you calculate the t-statistic, you're going to use a different distribution to look it up in, a different table. You're going to use a table of the t-distribution instead of the normal distribution like you've been doing. And one difference with the t-distribution is instead of there just being one, you'll remember you looked up values of z, there was a table, you used rows for the first decimal place and columns for the second decimal place, but it was just one standard normal distribution. There is a different t-distribution for every sample size. And for every sample size, you're going to calculate what's called a degrees of freedom. And for a one sample test like this, it's very simple. All it is the sample size minus 1. And then you're going to use that to look up the correct t-distribution. Degrees of freedom is something, there are different ways to think about it, but it's sort of the amount the amount of extra observations you have to calculate a certain statistic. So for calculating a mean, you only absolutely need one observation to do that. So if you have two observations, you have one extra, you have 1 degree of freedom. So it's kind of the amount of extra data you have. Another way to think about it is if you were given this test statistic, how many data points could you take away and figure them out again to get that test statistic? So if you have a sample size of 10 and you know the mean, you could take away one of those samples and then just try different values and figure out what that one observation was, because anything else will give you a different mean. It's not always intuitive, though, the degrees of freedom. The important thing is just that you know how to calculate it for a given test. And it's useful to know how to calculate because it will tell you if your statistical software is giving you a wrong answer because you're accidentally using it incorrectly. If you know how to calculate the degrees of freedom for a t-test, and then you see that in your SPSS output it says something different, it might be because you've made a mistake. And there are cases where that happens. Most common case is where you are trying to use a categorical variable, but it's been coded as a continuous variable, and you do a regression, you'll have the wrong number of degrees of freedom. And the only way, or the most direct way to figure that out is by doing a little calculation yourself of what the degrees of freedom should be and comparing that to your SPSS output. So, and sometime later, I'll provide a summary of how to get degrees of freedom for several different tests. But for the one sample t-test, it's just n-1. So there is a different t-distribution for each sample size, but all of them are symmetric about 0, and all of them are bell-shaped. So they look kind of like a normal distribution, but the thing is that they're wider than the normal distribution. And the fewer degrees of freedom, the wider it is. The more degrees of freedom, the more narrow it is, and the more similar it is to a normal distribution. So in fact, if you get up to a really big sample size, n equals 1,000 or something like that, it'll look basically identical to the normal distribution. And as you get down to n equals 4 or something, it looks quite a bit wider than the normal distribution. So, and you can think about this kind of intuitively in that, remember when we knew what the standard error was, we could calculate, we knew what the variability of sample means would be. Now, when we don't know exactly what the standard error is, because we're estimating, we don't know the true standard deviation, we have to estimate it from the sample, there's actually more variability that you can get in your calculations of t, that difference in means divided by the estimated standard error, because you have some error in the standard error as well as variability in the mean. So you remember, in this, the x bar minus the mean under the null hypothesis divided by the standard error. Before, when standard deviation was known, we only had sampling variability in this mean. Now we have sampling variability both in this mean and in this standard deviation. So the values of t can vary even more. That's why it's a wider distribution. And why the fewer samples that you're using to calculate S, the wider the distribution is. This is just an example of what this table looks like. And here we have, for every row, a different number of degrees of freedom. And so as a result, you can't look things up as exactly, and the tables tend to only give you the critical values of T for common alphas. So you can look up what the critical value is for an alpha of 0.05 and any number of degrees of freedom, or an alpha of point of 0.01, for example. So it doesn't allow you to actually calculate a p-value from your sample. It just allows you to decide whether or not to reject the null hypothesis based on whether T exceeds your critical value. So degrees of freedom, it's your sample size minus the number of things that you estimate. So if you're estimating the mean, you lose 1 degree of freedom. Yeah. Yeah, it will start changing, especially when you do analysis of variance, where you're estimating the means of multiple groups. Each one of those, you lose a degree of freedom. There's that alternative explanation that I mentioned, that if you know the value of your statistic, like the T statistic in this case, how many observations can you take away and then replace them again? We use the T for normally distributed populations. That's an assumption that we have to make in order to use the T distribution. So whereas with a very large sample size, you'll remember it didn't matter what the population was distributed like because of the central limit theorem. Central limit theorem doesn't apply anymore because it's a small sample. So we have to make an assumption about the population distribution, that it's normal. But you can use the T statistic to calculate a confidence interval just like you did before using the table of Z values. The only difference will be that value of T. And so for a 95% confidence interval, it's not just going to be 1.96. It's going to depend on your sample size. For a small sample size, this will be something bigger than 1.96 for a 95% confidence interval. And for hypothesis testing, rather than just calculating the p-value, if you're using SPSS, you just get the p-value. If you're doing it by hand, then you're going to calculate critical values of T and reject if the T from your sample is bigger than that. So there's the example with the brews. You have 5 beers, you measure the alcohol content of each of them, and you want to build a confidence interval for what the true mean alcohol content is going to be if you make 1,000,000 of them, and is there evidence against some null hypothesis. And there's enough data here for you to go ahead and do both that confidence interval and the hypothesis test. So just to remember your assumptions, that we have a statistically random sample. That's always an assumption of hypothesis tests we do. And additionally, for the t-test, that it is approximately normally distributed. We don't use it for testing proportions. We only make the normal approximation for proportions, and we only use them for large samples. So they are, however, robust to violations of the assumption of normality. And by robust, I mean that it will not cause you to make more type 1 errors. If your assumptions are violated, your power can go down, but you won't make more type 1 errors. So if you set alpha equals 0.05 and you have a non-normally distributed population, you're still not going to be more than 5% probable to reject the null hypothesis. Sorry, that's the property of conservativeness. Property of robustness is that some departure from normality is not going to have much effect on your test. It has to be a fairly strong departure from normality. And then on the next slide, I give some rules of thumb for that. With the exception that when you're doing one-sided test, it doesn't work as well as with two-sided tests. Another reason that we don't usually use one-sided tests. So here's some practical guidelines. If you have a small sample, less than 15, your data, your observation should be pretty close to normal. Once you get over 15, there can be some skew. And once you're over 30 or 40, you can have fairly strong skew and big outliers. And you use the tools that you've learned earlier in this course to assess these assumptions in any data set that you have. All right, so some quick Q&A, and then I need to let you get to lab soon. So is the t-distribution, does that describe a population or does that describe a sampling distribution? Very good. Describes a sampling distribution. So when we're estimating the standard deviation from the sample instead of knowing it from the population, do we use the t-distribution? Yep, that's true. I'll go ahead and so is the 95% confidence interval larger or smaller when you use T compared to when using Z? What's that? Larger. Yep, it's larger, or it could be approximately equal if we have a large sample size. It'll never be smaller though. And as I already gave you the answer, but tell me anyways, as n increases, the t-based confidence interval becomes more similar to the z-based confidence interval. True. Yep. All right. So we've taught you all about significance tests. Let's talk about some limitations of them. One thing to remember about the p-value is it tells you about statistical significance. It doesn't tell you about practical significance. So when you have a small sample size, then even big differences between your study population and your null hypothesis, you're not going to see. So that you're going to get statistically insignificant results, even if there is a practical difference. On the other hand, when you have a very large sample size, and you're going to find this with the New York City Community Health Survey because it's a pretty big sample, even small deviations from the null hypothesis can give you a statistically significant result. So just because you have a tiny p-value, you have a p-value of 0.000001, it doesn't necessarily mean that that difference is important in real life. It just means that it didn't happen by chance. And confidence intervals can be more informative to that because it actually tells you the size of the difference, whereas a p-value, that's just a probability. It doesn't have to do with the size of the difference. Oh, this is an example. So a paper about this called Too Big to Fail, large samples in the p-value problem, showing that for sales of cameras on eBay, there were various things. One of them here is What is this one? Some factor that you can change about what you advertise in a camera. It has a coefficient of 0.1, a p-value of 0, and the interpretation is here, oh, it's the minimum bid price. So if you increase your minimum bid by 1%, you'll get on average a 0.09% increase in final price. So we have a p-value of basically 0 here, but it's up to you to decide whether that is a difference that you care about when setting your minimum bid. That if you increase your minimum bid by 10%, you can get a 1% increase in your final price. Maybe it matters, maybe it doesn't. This is a big one, a common one. The p-value is not a probability that H0 is true. Very common misconception. Does anyone want to tell me why that's false? Okay, there's the answer there, but tell me in your own words. How about this example? Researchers did not find evidence of any effect of the treatment on self-reported pain because they got a p-value of 0.2. Does that mean there's an 80% chance that the pain reliever has no effect? Yep. Exactly. It just means that you don't have enough evidence to reject it. Obviously, if you don't try very hard, you collect a small sample, you're probably not going to reject it. That doesn't make it truer. It just means that you didn't have evidence to reject it. Another way to say that, the idiom associated with this is no evidence of a difference is not evidence of no difference. And yes, although 0.05 is the common cutoff, it's not a magic value. There's not actually that much difference between a p-value of 0.04 and a p-value of 0.06. And one case where this can come up is you often have studies that have more than one endpoint. So you remember that malaria intervention study? There was one endpoint that was anemia, one that was performance in math, one that was performance in spelling, and you can end up with, if they're correlated endpoints, a p-value a little over 0.05 and a p-value a little under 0.05. It doesn't mean that those are fundamentally different. It just means you didn't meet that threshold of evidence for one of them. So, but when you're thinking about it yourself, 0.06 is still some evidence against the null hypothesis. If you were going to bet even money, you'd probably want to bet against the null hypothesis. It's just you didn't have that 5% probability against type 1 error. So another way to misinterpret hypothesis tests is to forget that they're about the central tendency of the population. So they're about the average of the population. And I had some questions on the last exam about this, just to emphasize that it's about the means of the samples. It's not about the individuals. So we measure serum lead levels in a sample of 100 children from an area with potential lead contamination, find a mean of 5 micrograms per deciliter, which is less than the normal limit of 10, and reject the null hypothesis, 0.01. So does that mean that fewer than 1% of children have serum levels exceeding the limit? What do you think? Yes or no? No. Hopefully, think about that until it screams out at you as no, because that's a really bad misconception. It has nothing to do with individuals. It's just about samples of size 100. It's about the mean. It's about the mean serum blood level of children in this area with potential contamination. It's about their average. It's not about how many individuals are below that level. Hypothesis tests are about averages. They're about central tendencies. So if n is small, n is 6, does that mean you can't believe any results of a hypothesis test? Or conversely, if n is 1,000,000, does that mean that you have to believe the results? I don't think so, no. So why not? Well, the big issue is it a statistically random sample? If it is, then we have these procedures that you've learned, the t-test, they will account for the amount of variability that you get in a small sample like that. So if there's a big enough departure of that sample mean from your null hypothesis, then you should reject the null hypothesis. Now, if you have a sample size of 1,000,000, of course, you get a smaller standard error. It's easier to get a small p-value. But what if that sample size of 1,000,000 is a totally biased sample? It doesn't actually represent your target population. Then you could still have a wrong conclusion. So it is better to have a smaller representative sample than a bigger biased or unrepresentative sample. Of course, your hypothesis testing, your p-value, do not control for biases in study design. And in my field, in cancer genomics, there have been some very high-profile retracted papers and withdrawn clinical trials for reasons about this, because there were flaws in the study design where a sort of interview bias where they used a different set of experiments on the controls than they did on the cases, so they got small p-values, but it was just because of technical flaws of how they did the experiment. That has to be assessed independently of your p-value. Remember, of course, that your tests can be statistically significant by chance. That's what you control with the type 1 error rate. This is a XKCD cartoon where they do the same study with 20 different colors of jelly beans, and then eventually find that the green ones are linked to acne after they've tried 19 other colors. So you'll learn later to control for that with multiple testing, but remember that with a p-value of 0.05, even if no jelly beans are linked with acne, by the time you test enough of them, you'll get a p-value under 0.05. What you read in the literature, about the difference of an effect size, very oftentimes the true difference between their target population and the null population will be less than what's reported. And that's because of a phenomenon known as publication bias, which is that it's harder to get studies published if you don't find a difference. So it's also called a file drawer problem, that the studies that don't find a difference, they get filed away. The ones that do find a difference, they get published. So even if it's no fault of the researchers who performed that study, that kind of bias can result in this sort of lifting of statistical significance and differences seen in the published literature. And it's really once you have some replication by independent researchers that you start to get an accurate idea of what the difference between this target population and the other population really is. And there are some high profile examples of this too, especially in drug trials. We're a little more careful now about drug trials, at least those that get approved by the FDA, but in other types of trials, there aren't those kinds of protections to protect from all of the different drugs or all of the different studies that didn't find statistical significance just not getting published. Okay, I can let you go to lab now.